Hey guys, welcome back. In this lecture, I'd like to talk about the geometry of the dot product. So let's suppose that we have two vectors in space, some space. Let's just say, in our minds, let's think three-dimensional space, but it could be two-dimensional, four-dimensional, or whatever. But let's say that these two vectors are somehow in different directions. So we're at least in two-dimensional space. And so let's say we've got our v and our w. And what we would like to do in this lecture is determine, so first of all, before I state what we want to do, just think about this. If you have two vectors in space, those two vectors kind of pick out, they're either in the same direction, which these two are not. We specifically chose this so that they're not in the same direction, or those two vectors are in different directions, right? And if they're in different directions, then they span like a plane. They live in the same plane somehow. And we can always pick up our vectors and move them around so that they share the same initial point. Once we do that, then those two vectors determine that plane, right? They determine the plane that they live in. And if two vectors live in a plane, then we can start talking about the angle between them, right? So even though these might live in a higher dimensional space, they are essentially living together in a two-dimensional subspace. We don't need to get into the details of all that, but the idea, though, is that it makes sense to ask about the angle, we'll call it theta, determined by these two vectors. All right. I drew the angle that we want to find, this angle theta right here. But this is not the only choice for the angle theta, right? If I'm measuring an angle from V to W, I can do this one. Or I could have done this other one, right? I could have gone around this way and measured this angle. Or I could have just gone, around and around and around. The angles, especially, we always use radians in calculus, but angles are not unique in that sense, right? But we're going to make them unique. So we are going to restrict that we want to always find the smallest angle between two vectors. So this angle theta, this is our goal for the lecture here. Our goal is to find the smallest angle theta. So the smallest non-negative angle theta between these two vectors. So determined by or made by these vectors, v and w. All right, so this is what we want. Now, one thing that we can do is we can, when you have, I'm going to erase this, this angle that we don't want and get it out of the way. So one thing that we can do if we want to try to find this angle is we can say, okay, we see we've got these two vectors, they form like two sides, right? Two sides of the angle. We can close off the third side, right, by just connecting these, because these are not just, they have length, right? The vectors have length. And so one way to do that, well, you always do this, right? But if we're working with vectors, we want everything to be a vector. So if we put the tip of this vector here, then this becomes the difference vector, w minus v, the way I've drawn this right here, right? All right. So at this point, we now have a triangle. We know two sides of the triangle, v and w. Really, we could then compute the third. We know all three sides, right? And we want to find this angle right here. So at this point, we can apply the law of cosines. So the law of cosines, I'm sure you remember, looks like the following. I'm going to draw a picture here that looks pretty similar to that, and then we'll try to copy everything that we need. So here's a triangle. By the way, this is not a right triangle in general. Let's call this A, B, C. So these side lengths are opposite, right? A, B, C. And we want to find this angle theta right here. So this angle theta A can be called, sometimes called the angle A, capital A, right? So what we end up with then is that the side opposite this thing, so the square of the side opposite this, so A squared, is equal to B squared plus C squared. That looks like the Pythagorean theorem, right? But that would only hold if this was a 90-degree angle or a pi over 2. I just said we're only using radians, right? If this angle was pi over 2, but this angle, I mean, in this picture, it's definitely not, right? It's not pi over 2. So what we need to do now is adjust, right? So this is then minus 2 times b times c times the cosine of the angle theta, which in this case is the angle A. All right, so there's the law of cosines. Then we'll just work this out, all right? But we're going to apply this now. So let's see what happens here. So by the way, if we're looking at these sides, at these vectors, and considering them as sides of a triangle, then the lowercase ABC in this picture are the lengths of these sides, right? So what we need to do now is go back to our triangle up here and add the lengths. Add these lengths. And then we'll remember from the last lecture that we have formulas for some of these things. So let's first write out the law of cosines for our triangle. So our triangle says that, start with the orange, so the length of w minus v, quantity squared, the length squared, is equal to the sums of the squares of these lengths, so the length of side v squared plus the length of side w squared, vector w, right? And then subtract off 2 times the product, length of v, times length of w. Green, I'm trying to color code this, and then sometimes gets confusing for me. And then times the cosine of, I went too soon, cosine of our angle theta here. All right, and so this is what we want to work out. Now, we can do a couple of things. So let's recall. So this is our formula, right? This is our formula for the law of cosines on that triangle. We want to learn something about this angle, and we're going to learn something else extremely interesting along the way. But that angle theta, that's our goal, right? Remember, our goal was to find the smallest non-negative angle here. So that's our goal. Let's recall a couple of things from the previous lecture. So recall, first of all, that the length of a vector squared is equal to the dot product of that vector with itself, right? V dot v is the length of v squared. That's going to apply to all of these squares if we want it to, all right? If we want it to. We definitely want to do it on this side, this v minus w, all right? And so when we do that, we remember that we also have a distributive property, right? So if we wanted to do like vector a plus b dot product with vector u plus v, I guess, different, right? Then these distribute, and the dot product is treated just like multiplication of numbers in this case. So you get a dot u plus a dot v. This is just the distributive property, right? B dot u plus B dot v. All right, so let's use both of these ideas to now simpler work out. It's not going to look simpler, but we're going to expand actually this term right here, right? So therefore, we'll say now this w minus v, quantity squared. This is the same as w minus v dot product with itself, right? And then we can apply this distributive law to this difference now. And this is a difference, so we have to be careful about the signs, right? But we end up with w dotted with w minus w dotted with v minus v dotted with w plus minus minus plus v dotted with v. All right? And at this point, we notice a couple more things, right? W dotted with w, well, that's length of w squared. V dotted with v, that's length of v squared. So those two things can be simplified. And so over here, I'll write this as length of v, quantity squared. And in between, we notice we have two copies of these things. One's w dot v, the other one's v dot w. So this should be another thing we need to recall up here, that the dot product is commutative, right? So v dot w is actually equal to w dot v. So this now becomes minus 2 w dot v. All right, so let's now put this in. So put this thing into our formula for this. When I say put it in, I'm going to rewrite the whole thing, and I'm going to stop color coding it. But we're going to plug this into this side, leave this side as it is, and then see what happens. So our equation becomes the following. So it's going to be length of w squared minus 2 times w dot product with v plus length of v squared equals, on the other side, it was length of w squared plus length of v squared. I changed the order. You can still kind of see part of it there. Minus 2 times the length of v times the length of w times the cosine of the angle theta between the two vectors. And now we can start canceling stuff, because look at, we've got a w squared here, we've got the same term here. They're gone. They're on opposite sides of an equal sign. They cancel out. Same thing here. V squared, they're gone. All right, and at this point, all we have is negative 2 w dot v equals negative 2 times this product over here. And once you have just this green, right, this is all that's left. There's no more addition or subtraction on either side. Once you have these equal to each other, then you see that the negative 2's are common factors. So those can cancel out, right? And so here's our first piece of information that we learned, and this is really useful information. we get this formula for the dot product, right? So we now learn that the dot product of W dotted with V, these are just generic vectors, so this formula is always going to hold, but W dotted with V is equal to the length of V. Let me change the order just so that everything's in the same order here. So let's say that this is V dot W. Remember, this is commutative anyway, right? But V dot W is equal to the length of V times the length of W times the cosine of the angle between the two. So remember, we motivated our formula, our original formula, for the dot product by trying to make sure that it was a representation of length, right? That we could represent the length of our vector by this formula right here, right? This was like our motivation for writing down the definition of the dot product in the algebraic sense. Now what we've done is seen that, okay, we also get a representation of the direction, or at least the relationship between the two directions of the two vectors, right? The theta. So these two, this angle right here that the vectors make with each other, this angle plays a large role in telling us what the dot product of these two vectors is going to be. All right, and this is it. This is the formula. So that's the formula for the dot product. You can use this as long as you know the lengths of the vectors and the angle that they make. Notice that the orientation of the vectors doesn't matter, right? So, you know, in some sense, what direction any individual one of them is pointing doesn't matter. What matters is the relationship of how they are pointing with respect to each other, right? So the directions with respect to each other. All right, from here, though, we still haven't answered our original question, which was to find theta, right? We want to find theta. So from here, we have to rearrange dual algebra and solve for theta. It's not too much work, though, because, well, by the way, this formula always works, although it wouldn't necessarily, you have to be careful, right? So if what I should have assumed here, I drew two vectors, neither of which was the zero vector, right? So I didn't draw the zero vector, but I should have said at some point that neither of these are the zero vector. So V and W are not the zero vector. The zero vector, remember, does not form an arrow. The zero vector is just a point. It doesn't have a direction. So it would be impossible to think about the angle that's made between a zero vector and some other vector. So this formula right here, as it's written, only applies to non-zero vectors, but it turns out this works for all vectors V and W that are in the same space, right? So V and W in the space Vn of all vectors. Now, it's easy to see why the zero vector works, because if you plug in the zero vector for either one of these, you're going to get 0. The length of the zero vector is 0, so these are gone as well, right? So 0 equals 0 is, of course, true. So this holds for the zero vector. It also holds for all other vectors. That's the important part. All right, so now when we want to solve for theta, though, now we have to be sure to say that neither of these vectors are 0. All right, so for V and W, both non-zero vectors, right, then this means in particular that their lengths are not 0. So the length is not 0, and the length of W is not 0. That's important because our first step is going to be to divide through by each of these numbers, right? So we have, at this point, the cosine of theta is equal to V dotted with W over the length of V times the length of W. Again, we're not dividing by 0 here because we've made this assumption, right? And then so that's a formula that involves the theta, but to get the theta out of there, we can apply the arc cosine. All right, and so this is our formula for the angle made by two vectors. So the arc cosine of this ratio, V dotted with W over length of V times length of W. And remember that the arc cosine gives us a angle, theta, that's between 0 and pi, right? So that's exactly what we wanted, the smallest angle between two, 0 and pi. So if you think about the unit circle, right, here's the unit circle. Start here, cosine is 1, arc cosine works on the top half of the circle, right? So the arc cosine works on the top half of the circle. Okay, so how exactly does it work? Well, it takes in, remember how it works. So the arc cosine is going to take in this number. So this right here will be that number, thought of as a point on the x-axis, and then the arc cosine will go up and say, all right, You gave me that point, I'm going to give you back this angle theta, right? So when you give me this point, arc cosine gives you back this angle theta, which connects the point on the unit circle here, this opening right here, right? So, all right, so this is how the dot product can be used to compute the angle between two vectors.